Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at similitude. So first of all, what is similitude? Now let's say that you are designing a pump and you want to know the pressure drop that occurs inside that pump. And unfortunately, the pump that you are designing is very big. Let's say that the diameter is about 2 meters. The pump that is this size costs hundreds and hundreds of thousands of dollars. So how can you find this pressure drop? One thing that you can do is you can actually model that pump. Maybe the original dimension is 2 meters. Maybe you can make a mini pump or a model pump that is 20 centimeters and then test that pump inside a laboratory and find the pressure drop for that model pump. But how do you know that the parameter that you got inside the lab correspond well with the actual pump in the real world? And that is why similitude is important. Similitude is actually a way for you to create a model from a prototype. So first of all, let's differentiate what is model and what is prototype. So prototype is the full-scale object. And a model, it could be smaller or bigger than the actual prototype. Okay, so prototype is the real thing, but the model is something that you use in the lab. So usually if you are designing something big, a car for example, and you want to test it inside the wind tunnel, but your wind tunnel is not that big, so you would reduce that prototype car into a smaller model that could fit into that wind tunnel. So in order to make sure that whatever data that you get from the model correspond to the data that you expect from the actual prototype, this model need to satisfy a few similarity concepts. First of all is called the dynamic similarity. The dynamic similarity requires that the force that is acting on the model has the similar ratio with the force that is acting in the actual prototype throughout the entire flow. Let's say that the model that I'm testing has pressure force. So the pressure force of the model divided by the pressure force of the prototype must equal to a constant. And let's say this model is also subject to viscous force. So if I write here viscous force of the model divided by the viscous force of the prototype must actually equal to a constant value. And that is how you achieve dynamic similarity. It has to do with the ratio of the forces between model and the prototype. The next type of similarity that you need to satisfy is kinematic similarity. And kinematic similarity means that the velocity ratio or the ratio of the velocity between model and prototype has to be constant across the entire flow. This means that if you have an aerofoil of a model, okay, and this is the aerofoil of the actual prototype. When you have kinematic similarity, it means that when you plot the streamline of the model, it has to be similar with the streamline of the actual prototype. Okay, meaning that the ratio of the velocity at each point that you are studying between model and prototype has to be similar. So that is the second requirement. And the final requirement is geometric similarity. And geometric similarity simply means that, let's say you have the aspect ratio of 2/1 for the model. Okay, it means that for the prototype, you may have the aspect ratio of 10/5. The ratio of the prototype or the shape of the prototype must be similar with the shape of the model. So when you satisfy these three similarity principles, which is dynamic, kinematic, and also geometric, it means that whatever that your model is predicting, you can simply convert that prediction. You can simply convert that value, for example, drag or pressure drop, into the actual prototype using the appropriate ratio. Now let's take a look at a few examples so that you can familiarize yourself with this concept of similitude. But before we go into doing this example, there are a few things that you need to know. Basically, there are a few types of flows that is suitable for dynamic, kinematic, and geometric similarity. And quite often, you cannot satisfy all three similarities. So you can satisfy only some, but you have to find another method to satisfy the other type of similarity. It depends on the types of flow that you are working on. So first of all, let's take a look at a confined flow. So the simple definition of the confined flow is that this flow has no free surface and it is confined only to a specific region. Now, a confined flow does not necessarily mean internal flow. It could also be external flow, but it is confined within a specific defined boundary. For example, if you have a flow around the aerofoil, that is external flow, but it is confined to the area close to the aerofoil and it has no free surface. A more obvious type of flow is flow inside pipe. So that is internal flow and it is also a confined flow. And there are actually a few factors or a few parameters that could influence flow in the confined flow. For example, we assume that gravity does not contribute anything inside the confined flow. So this is our assumption. Our assumption is that gravity does not affect the streamlines inside the confined flow. So we can say that the gravity does not influence the flow pattern inside the confined flow. Okay, so first of all, no gravity. And the second one is that inside the confined flow, viscosity could be very important. So viscosity could be important. The next thing is that if the flow is moving quite fast, okay, then Mach number will become very important. But let's not go into that at this moment. There are also a few forces that are very important inside the confined flow, and these are what we call pressure force, inertial force, and viscous force. Now, if the ratio of these forces between the model and the prototype inside the confined flow is similar to each other, then we would say that this model inside this confined flow has achieved dynamic similarity. And because of this dynamic similarity, there are two dimensionless parameters that is very important inside the confined flow. First is called Reynolds number. I believe that you are already familiar with Reynolds number. So Reynolds number is equal to rho times velocity times diameter divided by mu, or simply velocity times diameter divided by nu. And another one dimensionless parameters that is very important in confined flow is called Euler number. And Euler number is EU equal to delta P rho v square. Okay, for some of you, this might be the first time that you heard of Euler number. Just know that this Euler number is important in confined flow. We will see this later in the example. So what happens now is, if you are looking to build a model that is using confined flow, then you need to make sure that the ratio of the Reynolds number and the Euler number between model and prototype is constant. Otherwise, what you predict in the model will not correspond to the actual prototype. Now, let's take a look at an example. Now, let's say that you need to design a water pump. Okay, and this water pump is very large that it can deliver the flow rate of 1.5 meter cube per second. So this is for the actual water pump that you are designing. So we're going to call this a prototype. And this pump has the actual impeller diameter of D equal to 400 millimeter. And this pump could deliver a pressure rise of 400 kilopascal. Okay, now obviously before you design this product, you need to model it and test it in the lab. And for the model, you need to do it with the pump with the impeller diameter of 80 millimeter. So D for the model is 80 millimeter. Now, with this model, what is the flow rate and the pressure rise that you can expect? Okay, so the question is asking for what is Q and what is the pressure rise of this model. So first we need to understand that this is a water pump and the flow inside the water pump is considered confined flow. And we know that for confined flow, Reynolds number and Euler number is very important. And let's see how we can use this to solve our problem. So first of all, Reynolds number of the prototype must equal to the Reynolds number of the model. Reynolds number of the prototype is velocity of the prototype times diameter of the prototype divided by the viscosity of the prototype. And this is equal to velocity of the model times diameter of the model divided by viscosity of the model. And if we are using water, it doesn't matter whether it's the real scale or if it's the model, then viscosity remains the same. So viscosity of the prototype is equal to viscosity of the model. And therefore, we are left with Vp dP equal to V model times D model. And we can rearrange this so that V of the model divided by V of the prototype equal to D of the prototype divided by D of the model. And this, we know the ratio because we know the diameter of the prototype and we know the diameter of the model. And this is simply 480. So this is 400 divided by 80 and this is equal to 5. Now I think only with this information, we can already find the flow rate of the model. Let's see how we can do this. Flow rate Q equal to velocity times area. And if I arrange this in terms of ratio, so this is Q of the model divided by the Q of the prototype must equal to the velocity model divided by velocity prototype times area model divided by area prototype. And Vm over Vp is 5. This is equal to 5 times area of the model divided by area of the prototype. Area is equal to pi d square. So this becomes d model square divided by d prototype square. And we also have the value here. This is equal to 5 times 1 over 5 square because this is dp over dm. What we need here is dm over dp and we need to square those. So this is equal to 1 over 5. And therefore, Qm over Qp is 1 over 5. And fortunately, we know what is Q prototype. Okay, so Qm is now, Qm is equal to Qp times 1 over 5. So this is 1.5 divided by 5 and is equal to 0.3 meter cube per second. And this is the answer for volume flow rate. And I think it makes sense, right? Because the Q of the prototype is 1.5 meter cube per second and the impeller diameter is 400 millimeter. Now that we are using 80 millimeter impeller for our model, of course the flow rate must be reduced. And what we got here is 0.3, so it makes sense. Now next, how do we find our pressure drop? We've discovered before that Euler number is also important. Now let's see if Euler number can help us solve this problem. So Euler number of the model must equal to the Euler number of the prototype. So now delta P over rho V square of the model must equal to delta P rho V square of the prototype. Now remember that we are looking for the delta P of the model. So delta P of the model must equal to delta P of the prototype times density of the model divided by density of the prototype times V of the model divided by V of the prototype square. And of course, rho is similar because this is just water. So delta P of the prototype is 400 kilopascal. This is 400 kilopascal times Vm over Vp. I believe we already have this. This is equal to 5. So the answer is times 5 square. So this will be 5 square is 25 times 400. This is 10,000 kilopascal. And this is the answer for our delta P of the model. But now you may be asking, you now have a smaller impeller diameter and you also have smaller flow rate. How come that this smaller thing can give you larger pressure rise? So this is the importance of similitude. Because you know that Reynolds number and Euler is very important, and you've plugged in the equation and you've plugged in the number, and this is what turns out to be. Now, even though it seems strange, a smaller pump has to deliver higher pressure rise in order to meet the demand of Reynolds number and Euler number. When this is satisfied, then you know that your pump model is working correctly. Now, that's it about confined flow. Remember, Reynolds number and Euler number is very important in confined flow. Now, let's move on to the second type of flow that I want to introduce to you, which is called the free surface flow. For free surface flow, the dimensionless parameters in order to connect the model and the prototype is going to be a bit different than confined flow. So free surface flow as the name suggests, is the flow that has free surface. And unlike the confined flow just now, where gravity does not affect the flow inside the confined flow, for free surface flow, the gravity does actually affect the flow. A few examples of free surface flow are dams, for example, flows in channels, or maybe it's just an object that is on top of the surface, and you want to calculate the drag, for example, that is also considered as the free surface flow. And because gravity plays a role in free surface flow, so affected by gravity. And because of this, the dimensionless parameter that is important in free surface flow is called Froude number. And we denote that as Fr, and Fr is equal to velocity divided by the square root of length times gravity. And for a few cases, Reynolds number is also important for free surface flow. However, Reynolds number is not as important in free surface flow as it is important in the confined flow that we studied just now. And also, if we try to match Froude number between model and prototype, and also at the same time we try to match the Reynolds number for the prototype and the model, as you notice here, the Froude number has the length inside the square root. But for Reynolds number, the length is actually outside the square root, meaning that it has the power of 1, whereas this one has the power of half. Immediately we notice that if we can match Froude number, we can never match Reynolds number. And if we match Reynolds number, we can never match Froude number. So this is the uniqueness of the free surface flow. You can only pick either Froude number or Reynolds number. And most likely we are going to pick Froude number, and we find the similarity of the viscous force through any other method. And we will see this in the example a little bit later. And now if we go back to our confined flow, we notice that for confined flow, pressure force, initial force, and viscous force is dominant. And for free surface flow, when the time comes, we can also use the ratio of these forces in order to achieve dynamic similarity. Now let's take a look at an example of the free surface flow. Okay, for this, let me write this for you. So example. And for this example, you are actually building a scale model of the ratio of 1/20. And you are to measure the drag of this scale model and then predict what is the actual drag for the prototype. Let me create a table here. This is model, this is prototype. For the model, the wave drag that you find is Fd equal to 27.6 Newton, and the speed where the drag is measured is 2.44 meter per second. And your task now is to find what is the drag force for the actual prototype and what speed that correspond to that drag force that you've calculated. Now, let's see how we can solve this. We know that this is the example of the free surface flow. And for this problem, this is actually a surface vessel. And of course, when you are studying a surface vessel, when you are designing one, you cannot just design and straight away build that vessel. You need to build a model in order to validate all your calculation. And this model is in the ratio of 1/20. And we know that for free surface flow, the Froude number is very important. So let's try to equate the Froude number of the model and prototype and see what it can get us. Okay, so first of all, the Froude number of the model is equal to the Froude number of the prototype, meaning that Vm over square root of LMGM equal to Vp over square root of LPGP, and gravity is of course the same, and we are looking for the velocity of the prototype, isn't it? Okay, so Vp is now Vm square root of Lp over Lm. And I believe we know the velocity of the model, that is 2.44 meter per second. And we also know the ratio of the prototype length to the model length, which is 20/1. So this is 20/1. And this means our velocity of the prototype is 2.44 square root of 20. This will be 10.91 meter per second. Okay, and I think this value makes sense because of course the velocity of the real vessel will be larger than velocity of your model. Now the tricky bit is to find what is the drag force. And we know that in order to achieve dynamic similarity, the ratio of the forces should be similar. But the tricky bit now is what force should we select? And for this problem, you can actually use what we call the inertial force. Okay, so let me write this for you here. We are looking for Fd. This is the drag force. So this is drag force of the model over the drag force of the prototype should equal the ratio of the inertial force of the model against the inertial force of the prototype. And the inertial force is given by rho times velocity square times L square. Now, if this is the first time you've seen this, I can imagine that you might feel a bit confused because you've never seen F equal to rho times velocity square times L square. But remember, we are in the topic of dimensional analysis. So let's take a look at the dimension first. The dimension for density is mass over length to the power of -3. The dimension for velocity is length over time, this is -1, this is square, times the dimension of length is length square. So in the end, you end up with m. This is L minus 3 plus 2 plus 2. So that will be L. And this is T minus 2 over T square. And if you notice, ml over T square, let's take a look at our example before. Isn't this the dimension for force? So even though it looks strange, in terms of the dimension, the formula is correct. Okay, so now let's get back to our initial force. So I'm going to write here rho of the model times velocity square of the model times L square of the model divided by rho of the prototype times velocity of the prototype square times L of the prototype square. Okay, now of course rho is the same, so I'm going to cancel that out. Now, do we have the ratio of Vm over Bp? Let me rearrange this. Remember, we are looking for the force of the prototype. Okay, we are looking for this really. So let me arrange this so that it becomes Vm over Vp square times Lm over Lp square. And Vm over Vp is, I know that this is my Vp, I just calculated that. This is my Vm. So 10.91, sorry, this is 2.44, is it correct? 2.44, yes, that's correct. 2.44 divided by 10.91 square. And Lm over Lp, remember that the ratio is 1 to 20. So this is 1 over 20 square. This is equal to 2.44 divided by 10.91 square divided by 20 square. And this gives me 1.25 times 10 to the power of minus 4. So this is the ratio of the drag force between the model and the drag force of the prototype. And remember, we are looking for the drag force of the prototype. And I expect that the drag force for the prototype is going to be very big. So Fd of the prototype is equal to Fd of the model. What is Fd of the model? This is the force of the model, 27.6. 27.6 divided by 1.25 times 10 to the power of minus 4. And this gives you 220.7 kilonewton. And 220.7 kilonewton is really big. And it makes sense because the length of the actual prototype vessel is going to be 20 times longer than the length of the model that you are testing now. So of course, the drag is going to be higher for the prototype. Now I think with this example, you can see that the free surface flow is a bit different than the confined flow. The dimensionless parameter that we use is different between each other. And of course, there are many other types of flow where we use another types of dimensionless parameters to solve them. But for this syllabus, we only cover two types of flow. That is the confined flow and also the free surface flow. And as usual, feel free to repeat this video again and again until you understand the principle of similitude. That is all from me for now, and I'll talk to you soon. Bye!